תודה רבה. וזה מוקלט?
כן, תראה לי רגע.
כן.
אתה רוצה לרשום את הפרטים של הפגישה הזאת? זה כל הזמן זה קבוע.
המספר הזה.
כן.
זה בדיוק איזה שאתה רוצה. כן, זה כמו שסנפל מוריד. אני תפן שנה שעבר.
967
הייתי חייל.
0651
עשיתי ככה.
6086.
כן,
סיסמה היא 2
נראה לי ממחזרים.
973. זה קבוע.
אבל 9 אני לא צריך לדעת בעיקר.
שיהיה
לי, אבל
כי אם אתה לא עושה מהמחשב שלך ואתה נכנס למחשב אחר, אז אתה צריך לדעת.
לא מספיק שאני עם הסדר שלי?
אם אתה לא נכנס עם היוזר שלך, אתה נכנס עם יוזר אחר.
ואיך אנחנו שומעים. זה מה שנשאר?
אני יודע כאילו אנשים שלא באים להרצאות או נמצאים באוטובוס. בדרך מוצא נכון.
מישהו בדרך? לא. So you don't speak Hebrew, yes? I remember. Okay. $25% increase. So another minute. Maybe another 20% increase.
What is the student turnover in general?
No, I mean, it's a good for people in the course of 5. So, nice. Or we can start. Before 2 minutes. But if you have questions, you can start with questions. No questions? I want water. Question. Okay, so last time I was not accurate. So we talked about 2 different notions of image in general category and image in abelian category, and they are equivalent, but one has to be more accurate in what sense. So now you have map from X to Y, and say if you're working in a general additive category, this map might have image but it might be that it will not have co-kernel or the co-kernel will not have kernel. So it kind of easy to construct a stupid example. If you exclude some dimensions, and you say all vector spaces of dimension not equal to 1. And then if the co-kernel is one-dimensional, it will not exist. But the image might be perfectly off. So in fact, what you need that if you have a category which have kernels and have co-kernels, and this is called pre-abelian category, and then it's have images, and the image of the classical like in the general sense is equal to the canonical to the kernel of kernel. And of course the same for coefficient. And it's a bit less trivial than I thought, so let's make it from an exercise to a guided exercise. And so first of all, and this is not trivial thing, you want to show that if you have a mlet field, and then you consider from X to sorry, yeah, go ahead to the field. That's what you see. And then the co-kernel thing equal to this. So this is probably the hardest part, and I think I can do it, but we need to use, or at least maybe you don't have to use, but at least proof time in mind, we need to use existence of kernel and co-kernels you need to use the existence of this co-kernel. You can just, or at least I don't see a way just to prove that it's 0 without knowing that it exists. And if you know it exists, then it's rather easy to show. It has to be equal to 0. But I don't see now a way to show this. And then you want to show, okay, and then you make a criterion from that to be an epimorphism. This is the first step, or the hard step. One. So epimorphism means then x to y, when it's epimorphism, when for any z, or for any two different maps like this, these two maps are different. The two compositions are different. And, or in other words, that map from this home to this home is one-to-one. So this is epimorphism. And you know, like or algebra, how to prove that a map is a one-to-one map. You don't really need to run over any two pairs of elements. You just need to show that it doesn't map non-zero elements to zero elements. Or if it maps something to 0, then it's 0. And this is true for abelian or for groups, or for abelian groups in our case. It's not true for sets, because that makes sense to sets. It's not true for pointed sets, because it makes sense in drawing to pointing sets. And it's even not true for semigroups. This don't see why it should be true. I'm pretty sure it's not true. So if your category is actually additive category, then the Hom spaces are groups, abelian groups. And then you can say that if this is 0, then this is 0. So you can check only this condition. This condition, of course, if the map is epimorphism, then this condition is satisfied, but the other way around is not. So now you have a condition for epimorphism, and then you deduce from this condition that if a co-kernel of a map is 0, then it is additive. And so, and this will give you the second part. Okay, so this was the second part, maybe, which I explained how to do. So, criterion for being epimorphism in additive categories. The third part is that the map C here is epimorphism. And yeah, this is the hardest part of proving that there is a. Here I wrote image, but maybe I should be more accurate. Yeah. Cool. Image is the definition of additive. And now we want to show is that is it image in, so we have factorization x, y. Now we can take here the image in the sense of additive category. We have factorization, and this map is isomorphism. So we only need to show universality of this factorization, which is easy. So therefore, it shows that. Yeah. Okay. Image. This is definition of image in additive categories, and this here I mean image in general category. Okay, are we good with this exercise? Guided exercise. Okay. So let's go to functors. So last time I defined functors and defined Boolean functors, yes? I did ask you what you did last time in the exercise. In the TPA, in the what you would do.
Last time, we did the natural
Okay, so
and additive category.
okay. So okay, so if what I'm saying now already was in the exercise session, just tell me like this. So examples of functors, probably the most common example of functor is forgetful functor. You can forget some structure, or you can forget some information. So in mathematics, we often, not all categories, but many categories defined like this. We have some theory, so we have some set, some operation, some structure, and then some axioms, some information. Now you can erase some of the axioms and say, okay, now we don't require it anymore. And it means that if you have objects that satisfy this axiom, it also object that does not have to satisfy this axiom, so you have functor between one category to another category. Or you can say, I don't need this structure anymore. So I have it, but I ignore it. So I have a map, I have a functor from the category of object with structure to category without. So from this point of view, in the bottom of everything lies the category of set, and every reasonable category or every category which is classically used in theories have a functor of sets. So we have groups, two sets, and we have rings to sets, and topological spaces to sets, symmetrical spaces to sets, vector spaces to sets. These are all forgetful functors. Forget them. Now here in between you have, for example, monoids. And you see that the forgetful functor set, you can break it into two steps. This often with forgetful functors, you can forget things in steps. And you can forget the axiom of immutability and don't forget and then forget the structure of multiplication. You cannot do it the other way around. Now, here is something that might be a bit delicate. What is the structure that you're forgetting? What is the axiom? So it really depends on how you write the axioms down, and there is no one standard. Yes, so groups are the inversion is part of the structure, or just axiom of existence of thing. So it doesn't really matter in this case because of several reasons. But basically, the inverse is uniquely defined, so we can say it's axiom and not a structure. But if we're going to say semi-groups, so groups that doesn't not necessarily have inverse, but also not necessarily have unity. So unity, it's still, we usually used to think about it as an axiom and not a structure because unity is uniquely defined if it exists. But not any homomorphism of groups that or semi-groups preserves the unity. So okay, here we have semi-group. And we have here functor. And you can think about this functor as forgetting forgetting axioms and not structure. But it's better to think about this function as forgetting structure because the unity, although it doesn't have to be part of the structure, but it is part of the structure when you define morphism. And for categories, morphism is important part of that of what you do. But we still call all of them forgetful functors. So the fact that functor is forgetful is not a mathematical statement because it depends on how you define these categories and how you think about this functor. But if you work in a context of sets with structures, then it's rather clear what is going to be forgetful functor, but it's not always clear for the context.
What I don't understand is we have a monoid, give a monoid, it has a unity. Then we forget about the axiom of the unity element. Then what happens to that element in the semi?
It's still there.
It still
But
acts like a unit.
it's the any monoid, it's also a semi-group.
So it's the
It's having unity, but it doesn't have to have them. So it's the same object, but in a different category. If we define the category of semi-groups as sets with operation, which is associative, and category of monoids with sets with operation, set with which is associative and an existing unit. So just don't change anything, just take the same object and consider it as
So in the semi-group, the unity will still function as a unity, just doesn't have to be.
yes, yeah. Now, if you define when you go to sets, then you start with set with operation, then you forgot about the operation, so it's left with a set. So if you define monoid like a set with operation and with an element which you call unity, such that some axiom satisfied, you can then the forgotten functor say it's a set with operation, and you don't mention who is a unity anymore because it doesn't matter, it's still set. You wanted to ask that? So of course here we have vector spaces. Here we have a billion groups. 1 billion groups of groups. We can forget the fact that there are billion. Here we have vector spaces. But sometimes we're not really sure what is the functor, what is the forgetful functor. So for ring we have a nice forgetful functor, so billion groups. But depending on the context, you want also to consider functor to say semigroup, multiplicative semigroup of everything. The element you forget everything except for multiplication. This is okay. I didn't discuss what the commutative diagram of categories, but certainly this should not be commutative diagram. Yes, because you start with a ring. Here you will get the additive structure, and here you get multiplicative structure. So you have two different functors from rings with only groups, both of which you can call forgetful functor depending on the context. So when you say consider them forgetful functor from one category to another, sometimes it's okay, but sometimes you need to specify what you actually mean. Okay, you have topological spaces, the sets, and you have metric spaces. So here, formally speaking, it's not a forgetful functor because you don't just forget the metric, you forget the metric, but you remember the topology which was not there yet because metric spaces did not define the metric spaces, not topological space. But you all know that once you have topology, metric, you can construct a topology out of it, and you all know that the metric is like more delicate information. So it's perfectly okay to think about this functor, forgetful functor. And here in between, you have metrizable spaces. Yeah, so here is a case when you first forget the structure, but remember something else, like the fact that it exists. And then here you forget only axiom. So they're both forgetful functors, but this like forgetting values. So metric spaces we discussed it. It's not clear what is the category of metric spaces, there are several versions, but all of them have functor topological spaces. And topological vector spaces. So it's this. And in between we have Fauché spaces, which are okay. First, F spaces, which are the same as topological metric spaces, topological vector spaces, which are metrizable, and Fauché spaces, which are local convex vector spaces. So somewhere here you have locally. So you have lots of stuff you can do. Yeah. Again, so here we usually think the forget functor goes this way, but in fact, if you start with vector space, you always can consider. No, maybe okay, maybe it's not a good example. Maybe a better example. You consider this functor. That's what political space into sets. We usually think that so forget functor going this way, but you can consider sets as discrete topological spaces, and often it's a convenient way to think about it. And then you have the nature functor the other way, which we often we think about as kind of forgetful functor too. Like you forget the axiom of being discrete. Not very common, but sometimes it's nature way to think about it. Okay, so you have lots of forgetful factors. Let's do some more into those.
We say that some of these functors are injective, and we actually forget some structure if the functor is not injective.
Yes and no. So there is no notion of injective functors. There are two competing notions of what is injective functor. I will discuss them, but I already will say now because you asked. There are faithful functors and fully faithful functors. Like both fully faithful is stronger statement than faithful, and both of them can be thought as analog of injective. So forgetful functors are usually fully faithful. Like if they're not, then probably it's not a good idea to call them forgetful functors. If they're so usually faithful, so faithful. But if you forget only axioms and not structures, then they're fully faithful. What may be more intuitive to call injective. But they both have good case to be called injectives. So we will go back to it in a moment. Okay, another thing in terminology, and you enjoy terminology, what are functors? So today we just say functors, and there's just one reasonable notion of functors, or usually one. But once upon a time, there was two notions, covariant functor and contravariant functor. And so covariant functor is something that's mapped object to object, morphism to morphism, and like so. And contravariant functor is something that maps object to object and morphisms to the other direction, which we don't really need a new notion for that. We just can say it's a functor from the original category C to move to the opposite of the target category. Of course, you can resolve here, I think. And the reason is that people use new notion for it because there was lots of examples of such things. But now we just say functor or functor of the category, but still we can use a notion of opposite of contravariance. And if it's convenient, but the default is covariant. And the basic example of contravariant functor is duality, say from vector space to vector. So here we have functor or contravariant functor from vector space to itself, or just covariant functor, usual functor from vector space to the opposite category, which for any vector space map it to the dual space. And morphisms are mapped to the dual morphism between the dual spaces, to which nature goes to the other direction. And if we restrict ourselves to the category of fine dimensional vector spaces, which is a full subcategory of all vector spaces, then this functor is equivalence category, which kind of rare case, or rather rare case, when a category equivalent to its opposite. And you probably will see in the future lots of examples of dualities of contravariant functors between a category to itself. It's very common. And usually when you consider the category like the most natural setting for it, it's not, the duality will not be equivalent. So category will not be equivalent to the opposite category. But often you have like some usual, like some nice subcategory in your category, like fine dimensional vector spaces, on which the duality is equivalent. And sometimes this is kind of the definition of a fine object, fine dimensional object, the objects whose, if you take second dual, you get the original object. Sometimes it's good idea to use it as a definition, sometimes. Okay, another functor that you always have for free in any category is the functor of home. Or more exactly, if you have some object x in C, you have home from x to something, and home from something. So homes are set. I say home, probably should say more. Yes, so I will try to stick to this convention. In general category, we use the notation more to denote morphism between the two objects, and in additive categories we will use home. Of course, strict convention historically, because morphism is just short for homomorphism, so so you can just use what short you use, but this is kind of the convention. I think most of the people use it, of course, so not everything. So you always have more home, and it's always a set. But so you have two functors like this. One of them is covariant, and the other is contravariant. And who can help me and tell me what who of them is covariant and who of them is contravariant?
The first one is covariant, and the second is contravariant.
Yes, let's see. So I was forgetting, but this is functor from C to sets. This is functor from C to C over sets. Or you can put the O either here or here. I think it's more common. Let's see why, because if we have a map from X to Y and the map from Y to Z, you can compose these maps. So we get a map between, so for any map from Y to Z, we have a map between the two hosts, which we what we want for our factor. And here, of course, there is no factor. Because this is just a home source category, so it's the same. It's basically the same factor for the opposite category. So you always have a functor to sets if you're given a more category and an object. And sometimes you will, if the category is additive, then you will have functor to abelian groups. So you will have more, you can consider the functor to set or home. Home we did maybe this is what is good about the convention. So we will know this is the functor to the category of abelian group, and this is the functor to the category of sets. And of course, you can start. Let's call it some nicer name, you know, more mix and more possible to see. And then you have the category C, the category of abelian groups, and the category of sets. Here you have more, sorry, com, and here you have sets. Here we have this forget the functor for abelian groups. We didn't discuss what does community diagram categories means, but let okay, since we did discuss on some level, we did say that there is a category of categories, which is not a bad category. And in this category, you can talk about commutative diagrams, which usually are called commutative on the nodes, to say that they are actually commutative on the level of equality. So composition of these two functor is actually equal to this functor. So functors you can compose, it's very clear how, just apply to the object and morph it in a sequential way. And this category, this diagram is commutative in very strong sense, like it's commutative diagram in the actual category of categories. This is a rare thing, usually you will not see it, usually you will see it commutativity in a weaker sense, which basically says that this composition is isomorphic to more. But in this case, you just have equalities. And sometimes you have the notion of internal home, or more generally home. Okay, let's talk about internal home. In some categories, you have home, one reasonable notion of home, which give you an object of this category in the same category. So you have usually noted by some graph of and what you actually want, say that x is fixed, so you want that this thing but it will give you a function against C and itself. And suppose you have some forgetful functor from C set. Depending on the context, it's not some, but to say that functor is internal home, okay, there is probably an axiomatic way to describe what you want from some internal home, but usually it's not something that you state as a mathematical statement. It's just you declare that you want to consider this functor as internal home, and one thing that you want to have some standard forgetful functor, and you have this functor, just the usual home, and you want this diagram to be commutative. Usually you don't want to be commutative on the nodes, but just commutative on the level that this composition is more to this. So probably the most basic example is the example of abelian groups. Home in abelian groups is abelian group. This is internal home. But you can also do some more elaborate examples of vector spaces. Home vector space is the vector space. Even non-additive examples like, and then you probably want to call internal more the collection of all maps between two topological spaces. And the nature of topology is the open form of topology. Are you familiar with the open form of topology? No. So if you have two terms of x and y, then you can consider all continuous maps between x and y. And for any compact set in X and open set in Y, you can consider all the sets all the maps which on this compact set map to a given open set. So the idea is that to be close, since open like the two morphisms are like kind of close one to the other, means that for a large compact set and for very small open sets, the difference is if there is difference, and is inside the open set. So it kind of makes sense. It's a topology where convergence is a uniform convergence on compacts. So in general, we don't have a notion of uniform convergence in topological spaces, but in compacts we have. So topology where you have a uniform convergence for compacts, and this is called the open compact topology. And this is nice topology on more x, y. You say why it's nice, but later. And so it's an easy internal forming the pretty goal of topological space. Any questions on internal home or home or more? Okay, limits and colimits. So we discussed the notion of limit, and limit is a procedure that starts with a diagram and give you an object. So this procedure is not just abstract procedure; it's a functor. So we have the category of diagrams of a given shape. So I did not define the category of diagram of arbitrary shape, but only the category of connecting diagram of a given shape. But it's very easy to define. Within 5 minutes, I will give another definition which makes everything much easier. So let's ignore it for now. And you have the functor of limit. You think that. Then this is the functor. What? Now, we want some some examples. So x times y, so the function of x maps to, oh, sorry. Okay, there's several functions here. We have function of x comma y maps to x times y, but for this we need to say in what category this pair is. So we have the category of C times C, which are just pairs of objects in C, and morphisms are just pairs of morphisms. In other words, just a category of diagrams of this shape. So you can have a functor of x. Also, if you fix x, you can consider the functor y in epsilon times y, perfect functor from C. So this you can do for products, of course you can do for co-products, and you can do for fiber products. Again, you can say that you fix x and we fix z, and then you have a functor y. Of z. This is a functor from the over category of z to the over category of z. But you can also consider that the functor from diagrams of this shape to c. So nice functors. Okay. This was the beginning, we can raise it. And from the pair of functors between the over categories. So if you have x and you have y, you have them. Then you have two nice functors from the over category of x to the over category of y, and the other way around. Try to do it. So let's start with the functor from cx to cy. This is very simple. Do you have a guess how to define nice functor from the over category of x to the over category of y? So what does it mean? You have objects in the over category of x. How you construct an object in the over category of y? Composition. So on the technical level, this functor is very, very simple. Just any object here, you can compose a map to y and get a new map to y, and this is object in the category of y. And of course, this is the way you define the functor on objects. And usually this we'll do. So when we want to define the functor, we just specify how it acts on objects, and we guess that there is only one reasonable way to extend this definition to morphisms. So, but it's not mathematically rigorous procedure, and if you write a paper, at least at the beginning, you have to be careful and specify how you do it. But sometimes it's like really obvious, so no questions. So on the technical level, this is a very simple functor, but if you remember that we think of the over category of x as family of objects which are parameterized by points of x, whatever points mean. Okay. Then this procedure kind of have non-trivial meaning when you talk about families, because like if you have a point in y, you want to ask what is a member of the family which is corresponding to this point. You need to consider the entire image of this point. And for each point in this image, consider that member of the family that assigned to its point. And then you just put them all together, integrate them all together. It's kind of an integral of objects and get one big object. So if y is 1 point, it means that you integrate all the objects in the families to get one big object. So this is very simple on the technical level, but for point of view of families, it is kind of non-trivial. Non-trivial procedure. רואים את זה טוב? is it seen well? Okay, let's do the other way around. So I have x, y, b. I want to consider a functor from cy to cx. What's the natural way to do it? Pullback is the fiber product, yes. X times b over. So we take the fiber product and then you consider this as an object of x. So from the point of view of morphisms and categories, it's kind of a much more complicated procedure than here. But from the point of view of families, this is kind of the simplest procedure because you have family of objects that are parameterized by objects in y, and you have a map from x to y. You say, okay, now I want to create new families. So for each point in x, whatever it means, you consider its image in y, and you take the member of the family that's assigned there. And this is exactly what fiber product would give you, say, if you walk over sets. And this is very common seen in category theory and in fact in lots of branches in mathematics, in geometry, or when you have some mixture of algebraic geometry, like algebraic geometry, but not only algebraic geometry. If you have two geometric objects, x and y, and you have a map between them, and you have some category which you assign to x. It can be the over category of x, like in our case, so it can be the category of shifts over x, shifts over b and groups over x, shift of vector bundles, category of vector bundles over x, and lots of some nice categories that you can assign to x. And once you have a morphism between x to y, you often will have two functors, to one direction, to other direction, which we over to say notation. This will denote by phi lower star, push forward with respect to phi, and this will denote by phi upper star, pull back with respect to phi. And in many settings, you will have this pair of functions. And I'm going ahead of myself and say that these two functors are adjoint functors. We will not discuss what it is. We will discuss it for the next lecture. But it's also often the case when you have functor to one direction, you will have some nice functor to the opposite direction, and this comes together with this job. Okay, so let's do some other examples of pullbacks. Yeah. And push forward. And let's do pullback with modules. So if you have a commutative or associative with an algebra A, you have the category of modules over A modules or modules over. You all know what modules over ring, yes? And if you have a map with A and B, then you have a functor for mod A, mod. So for mod B, we have it. This is a very simple functor. You just say that any module over B. Now you have an element of A. You want to know how to act on it. You just send it to B, and then it's even probably simpler when A is a subring of B, and then you just call it the restriction. But in general, it's better to call it the full. And if you talk a kind of special case, but also like analogous case, depending on how you think about it, if you have two groups, H and V, you have representations of G, you can restrict it or pull it back to H, get the representation. And you also have functor to the other direction. We will discuss it when we discuss the joint functors. And you can guess what it is. So here you probably know the functor to another direction is just induction representation. And here also says notion of tensor products that give you functor to another direction. Okay, so now at the beginning we talked about diagrams and it was kind of complicated. We say diagram is a shape of a diagram with a graph, and diagram is assignment of object to each vertex of the graph and the map for each arrow of the graph. And we create very nice language to draw in, but you usually like to draw graph. But it's not so nice language to formulate things rigorously. And here is another language which is more general and easy to formulate rigorously. It's not that easy to draw. And so now we'll talk about new notion of shape of diagram. Shape of diagram will be just a category, or say small category usually. So not crazy. This I don't want to but it's so if we have a category gamma, we can consider it as a shape of a diagram, and diagram of a shape gamma in the category C, with object category C, will be just by definition a function gamma. So this is very short and simple thing, and then there is no question what are morphism between diagrams, just morphism between functors, which you already defined, and when lots of the theory become like already developed because we know the notion of functors. And the only thing is you can ask, okay, now they will having graph. How we make the graph into a category? Like we usually don't want to draw diagrams like categories, but I don't know how to draw category. And for this, we have the construction of the free category generated by a graph. Okay. This. So this is a category whose objects are vertices of the graph, and morphisms are passes between two vertices. And I'm including the empty pass, which is a path from a point to itself, which doesn't do anything. And this will correspond to the identity map. And composition of passes give you position of objects. Yes, so it's sometimes it's misleading or weird. This category, the free category generated by this graph is very nice and small, and the free category generated by this graph is much larger because it's infinite. There are infinitely many morphisms from this object itself can go many times from down. And now, so this is a way to say what are commutative and what are general diagrams and what are commutative diagrams. So we can consider, I don't know, the free category commutatively generated by some graph. I don't know. It's not transportation. Neither of these are. Yes. And here we say that objects are vertices, and morphisms, you can say it like this: any passes, but two passes are equivalent if they have the same beginning and end, which basically means that morphisms are just like poset. Either you have an morphism or don't have, and in order to have a morphism, you need to have passes. Yeah. And then functor from this category to the category to some value category C is just commutative diagrams, diagram of a given shape with value in C. And of course, you have so if you have a diagram and you have a commutative diagram with the same shape, but you also get some functor from the category of commutative diagrams to the category of diagrams, just by forgetting the category is commutative. And now limit you can define not only for diagrams in the classical sense that we discussed before, but for any category of indices. So for any diagram which is indexed by a category, shape category, you can define the limit and the co-limit, and the definition is exactly the same as before. We will take 15-minute break. And so found telephone. Oh, you want to ask some question before?
What is the difference to find a limit without on a general category?
With the limit of the diagrams, whose shape is undetermined.
Limit of the okay.
So you have diag gamma e. Gamma is a category, usually a small one. Small also, formally small, but also intuitively small, but not too large. And C is your value category. And then you consider, so you, as before, you consider this
The limit of the diagram.
category gamma. So what does it mean, the limit of diagram? I define it for physical diagram with graphs, but you can do it for any category gamma. So you add a terminal object to gamma, so you start the category gamma tilde, which is just gamma with another object. We will be like, which will be by definition terminal, so any vector is any object have a unique map to this object, new unique map to this object. And then you take the initial objects in all extension of your original functor to gamma tilde.
Initial in the sense of
Initial
functors.
terminal.
Initial in the sense of functors, right?
In the category of factors. You have the category of functors from gamma tilde. Inside it, you consider the full subcategory of functors which coincide with your original functor on gamma. And here I say coincide using literally, so it's often not a good idea here. It's allowed because you just define some basic thing. So functors which when restricted to gamma are equal to the original functor. And then you take the initial option. Of course, there is a way to phrase it without talking literally, but without going really without. Other questions?
Yeah. Can you go over again the definition of the variable and control variable?
So covariant functor is what usually called, also they just call it functor. Functor from category one to another category, object to object, and morphism to morphism to the same side. Countervariant functor is something that maps objects to object, but morphisms it's mapped to morphism between the corresponding object but to the opposite side. So this is kind of cumbersome to talk about it like this. So the modern way to say it, that countervariant functor from C to D is by definition a functor from the opposite category of C to of D, and this is equivalent of just the same data and basically equivalence of categories, but much better than that. Just isomorphism of categories, but almost equality of categories. Like, so the category of these functors and the category of these functors are the same in more or less as strong as possible. They are not equal formally, but they are isomorphic and of course are equivalent, which means say what they mean.
מבחינה משהו, לא, אבל זה דתי, כאילו, שעושים מופיזם, לא, כאילו, לא פעם, היום נהיה, אני מבין למה זה עובד, כאילו, יש לך פה, אתה רוצה למצוא, נכון, אתה רוצה כאילו למפות את זה למשהו, צורה כזו, צרה.
נכון, אבל תאורטית אתה גם מקבל פה גם בהגדרה הזאת גם
מפה משם לבי.
כאילו, זה כביכול, כאילו, זה אינטואיציה, כן, ברור שזה עובד, כן,
כן, כן.
כביכול חזק, כן, לקבל פה אקסטרה משהו.
זה... רגע, מה יכול לעשות? קופורדר בעצם, מה יכול לעשות חץ מ... אז לא יהיה לי חץ מאליו ל-X, חץ מ-X אליו, זה יהיה הפוך. זה יהיה הפוך. סבבה. בסדר. אבל כן, אז כאילו נדבר שכל הדיאגרמות עם שייפ גמא בתוך ה-WSC זה כל הפונקטורים מהקטגוריה של הדיאגרמה הזו ל-C. אוקיי, אז הפונקטורים וכל הפונקטורים משם לשם. למה? מה זה פונקטור? איך הפונקטור הוא גם?
לא, זה כל, כאילו, כשהוא אומר פונקטור זה פשוט, זה מגדיר לך פונקטור, כאילו כל דבר כזה, זה פה. פונקטור מוגדר על...
כאילו יש לך גרף כללי, יש הרבה ורטיסיס וארוס, ואז כאילו הפונקטור אמור לעשות פשוט סאבסטיטוט לארוזימורפיזמים ולוורטיסיזם אובייקטים ניסים. כאילו זה מה שהוא אמור לעשות.
כן, וכל מה שעוברים לזה זה דרך הפרי. כאילו אתה בונה את הקטגוריה מהגרף, ואז באמת אתה יכול לדבר על זה עם משהו.
כן, אבל אז כאילו הוא אמר שאפשר לדבר על המורפיזמים של הקטגוריה של פונק גם נשיא. שהמורפיזמים בין פונקטורים זה ענן של טרנספורמיישן,
נגיד.
כן. ואז זה כאילו, איך זה מוגדר בזה? אז שיש...
לא, נראה לי נעשה פה קצת תציג לזה.
כי בסוף אני לא מקבל אובייקט ב-C, זה הבעיה. הדיאגרמה לתוך C, כלומר, אז לקחת את הוורטיס ולהכין אותם לאובייקט הזה.
כמו שדיאגרמה בסופו של דבר זה כאילו מה זה פונקטור? כי זה אומר תיקח את האובייקט הזה ותמפה אותו לאובייקט הזה ב-C ואת המורפיזם הזה ותמפה אותו למורפיזם. אז זה פונקטור, אנחנו מביאים לך פונקטור, כאילו דיאגרמה מגדיר לך פונקטור.
כן, אני יודע. לא, אבל הדיאגרמה עצמה זה אובייקט. צודק. נכון. הדיאגרמה היא הקטגוריה, לא האובייקט בקטגוריה.
כן, כאילו חשבתי להסתכל על דיאגרמה, יש לך שתי דיאגרמה, יש לך את הדיאגרמה הכללית, ויש לך דיאגרמה עם האובייקטים והמורפיזמים של C.
אז זה כאילו מנופק כל ורטקס לאובייקט,
כל ורטקס אבסטרקטי לאובייקט קונקרטי ב-C.
סבבה.
גם דרכתי את זה.
אז אנחנו יודעים בעצם מזה.
קצת הוא לקח את הצורה הכללית ואז הוא אמר לא, כי בעיקרון מה הרי ההגדרה, זה לא תופס לך לימוד, כן, או משהו שתופס, כאילו,
כן, כי כל השאלים שאתה צריך להוסיף עוד אובייקט לתוך הדיאגרמה הזו.
כן, אתה מגדיר את הגמא שלך, שאתה רוצה להתאמת, אז אתה מוסיף את זה,
כן, כן, כן.
אבל אין לך כל כלי של אובייקט מההגדרה הזאת. אז אתה כאילו אומר, תעשה את הפנקטור הזה, אז זה נקרא כמשל אובייקט, לא,
כן.
אז כאילו, צריך עוד משהו כדי להגדיר, כאילו, נראה לי זה לא נובע,
כן, כן, כן. זהו, ואני זוכר שהוא עושה כזה פנקטור מכל קטגוריה בסט על ידי זה שהוא לקח מור של X וטמפלט. אז מה זה בעצם אומר? זה כאילו, קח את X, ועכשיו איזה תעבור אותה.
אתה כאילו מקבע את X,
כן.
ואז עבור ואז אתה מעביר כל אובייקט ב-C,
לסט
לסט
וכל המורפיזם X עליו.
כן, ואז אם אתה חושב על זה, ההרכבה זה פשוט, כאילו איך אתה ממפה איזה מורפיזם, כאילו איזשהו מורפיזם, איך אתה פשוט מרכיב אותו אחרי, כאילו יש לך פונקציה, אם אני לוקח את זה, יש לך פונקציה נגיד A ל-X, ויש לך עכשיו את המורפיזם ל-X,
אז מה אם
זה בדיוק על זה שאתה רוצה לדעת. כאילו זה דבר טוב.
מה זה מיקרו? רגע.
יש לך, אוקיי, סליחה, יש לך פונקציה, נגיד, X ל-A, יש לך פונקציה, אתה מקבל פונקציה, יש לך פונקציה ל-X ל-B, יש לך פונקציה ל-X, סליחה, יש לך פונקציה ל-B, ואתה רוצה ליצור פונקציה ל-X.
נכון, אני יכול לעשות פונקציה ל-B.
כן, ואז אתה מקבל באמת פונקציה ל-X ל-B, שזה טיפול של ליצור. כאילו, אז זה גם טיפול של פונקציה. אפשר להסתכל שזה.
רגע, אבל כאילו, מה זה רלוונטי להגדיר את הפעמים?
לא כך מאוד המורפיזם. אז
לא, הייתה, עוד פעם, הסט שהולך עליו זה פשוט לא מורפיזם מ-X ל-Y, כאילו, נכון? צריך את Y על כל המורפיזם מ-X ל-Y, ואתה מורפיזם
זה נגיד לא בסדר.
כן, זה
אז
מורפיזם בין
יש מורפיזם בין X ל-Y.
כן.
אז יש לך פשוט באקסטנשן
So we can continue. Oh, you have a question?
Yeah.
What was your question?
Yeah, I didn't get the functor between C and Z, like there are more X. Obviously, it's exactly defined.
Over C and we have X and C. So we're gonna have Y to more X to. But this is not enough, we need to specify how we make more. So we go to the from Y to X to Z. Let's call it phi. And we need to construct more of them. So this is more. We need to construct more of them, which we call more X of phi, or more XY,
More X.
or more X. So we have an element here, alpha.
Then maps to the composition.
Yes. Alpha is from X to Y and phi is from Y.
Does it?
Phi is, no, sorry.
Is from
So
Y
maybe in
to
the
Z,
other direction.
and we have
Phi is from as well. So we first from alpha, then from phi. Yeah. And now you have to show that it's so that it's a composition to composition that just associative effect. Okay. אפשר לתת מזגן? How do we do it? לא, אי אפשר לתת מזגן. לפחות אני לא יכול. Okay. So in sets we have, so categories is like the next level of the set. So we have between sets we have maps, between categories we have functors, and like in we have a category of sets, but we have other categories which are on the same level, like groups, vector spaces are all like categories. But the collection of all categories is on the next level of the next categorical level. And in fact, so this is what's called two category. We discussed about the underscores, and there are other two categories. And the most basic of the two categories is a two category of categories. And the most basic of all categories is a category of. And so in sets we have monomorphisms, epimorphisms, and bijections. So categories will have three levels, or like more variety. You will have faithful, fully faithful, essentially surjective, which will be the analog of epimorphisms, and the analog of bijections will be equivalence of categories. So maybe we'll start with the end with an interesting thing, which is equivalence of categories. Efforts are. So equivalence of categories is a functor from C to E, such that there are functor G from that to that direction, such that and isomorphism. First we take A B, so this is functor from D to D. So we will have isomorphism to take the inclusion to D. Oh, yeah, so it's a little bit a matter of taste. You can say that equivalence of categories is this entire data, F, G, this isomorphism and for U1, U2. But usually it's not what we do. Usually we say that functor F is equivalence of categories if there exists G, U1, UT, U2, and such that U1, U2 are. And in many cases, you will have very natural and nice construction of F, and the other guys will be not so nice. And we will give examples, but first I want to say it's other levels. So faithful functor is a functor which induces a one-to-one map on the set of morphisms between two objects. Fully faithful functor is a functor that induces bijection on the level of morphisms. And essentially surjective functor, so we wanted to say it's kind of surjective, so any object in the target, you have an object in the source that will map to it. But this is not a good idea. Not a good idea because you don't want to ask quality between objects. So for any object in the target, there exists object in the source that map to something which is isomorphic to the object. So let me say everything. So this was the equivalence of categories. So faithful F faithful if y for more y y is 1 F fully faithful if F x y projection and F is essentially projective. So I will say it's safe in two ways. This but shortest way is F induces a bijection of the set of isomorphism classes. So let me write it into some notations. So if we have two categories, if we have a category, then we can consider the set of its isomorphism classes. This is set of object up to equivalence, which is just two objects isomorphic. If we have functors between two categories, so an exercise which I didn't tell, I should have done it like last time, that functor maps two isomorphic objects to isomorphic objects. And in more details, it maps isomorphism to isomorphism. This is very simple. So if we have two categories and functors between them, then it maps isomorphism object, isomorphism classes in the first category to isomorphism classes in the second category. So it uses such a map. So let's call this map ISO-F. So functor is essentially surjective if ISO-F is now let's say it in with less notations. So essentially surjective if for any x in D there exists y at C such that x and such that x is a morphic okay, so f of y is a morphic 2x. Okay, and now before we go to examples, very nice theorem. If a functor is fully faithful and essentially surjective, then it is equivalence of. This is a theorem, it's not hard, I will probably tell the proof in a minute, or both of the proof. But it uses axiom of choice. So if you don't believe in axiom of choice, so then it's not a theorem. So, you can believe it's not true if you want, but more practically, it means that if you have a very nice functor, which is fully faithful and essentially surjective, one can construct an inverse, but this inverse will depend on some random choices and often will not be anything that you can put your hands on. So let's give an example. Instead of proving this theorem, I will just give one example. We have the category of, say, finite dimensional vector space. And you know that any finite dimensional vector space is isomorphic to Rn. So let's talk about the category of all Rn's. So what are the objects in this category? We can forget about Rn, just number n. So ob will just do the collection of integer numbers. We will define the more between n and m in mat. Mat is n by m. I don't remember how many columns and how many rows, but you probably all know it better than me. And if we have three numbers, m, n, and k, then we need to define composition, which will be just product. So the size should be in such a way that the product will make sense. And so this is a category, and this is a category. This look like a toy and not actual category, like some combinatorial thing. And this is some nice categories that reflect some theorem. And so this call it C1 and this. Now, of course, you have a functor from C2 to C1 because you can start with C2 in this way. So for any integer number, we can construct a vector space Rn, and for any two integer numbers and a matrix, we can construct a map between the two vector spaces. So I claim that this functor is fully faithful and essentially surjective. So why it is fully faithful? Because if we have two matrices, two integers and m, we know that the correspondence that maps a matrix to a linear operator is an isomorphism, or it's a bijection. It's isomorphism of vector spaces, but in particular, it's a bijection. And we know that any map can be represented in a unique way by a matrix, any map between Rn and Rk. Here, the objects are integer numbers, so here in the image, only Rn's will be relevant. Why it is essentially surjective? Because any vector space is isomorphic to Rn for some infinite dimensional vector space, is isomorphic to Rn for some. So this functor is fully faithful and essentially surjective. So the theorem gives a map to a functor to the other direction, and which together forms an equivalence of the figure. And at first glance, you can say, you know what is a functor of the other direction. Well, starting with vector space, we can construct a number, just its dimension. Here it is. Well done. But not here. This is exactly where the place where we're cheating when we define a functor on the object and ignoring the morphisms. What's going on when you take two vector spaces and morphism between them? Okay, we have two integer numbers. How we construct a matrix? We need a basis. And you see, there is no reasonable way to construct this functor to that direction. But we know that there exists, and there is a way to construct it. Just use the axiom of choice. So here is a construction of the proof of the theorem in this special case, a construction of the functor of the other direction. You choose for all the vector spaces in the world, and you choose a basis. Each time somebody gives you a vector space, it's come with a basis. By the axiom of choice. Of course, axiom of choice is usually about sets, so let's talk about small vector spaces or vector spaces where all the set, which all the vectors are subset of some huge set, and 2 to the 2 to the 2 to the alpha. Probably would be enough. And then you choose a vector space, for each object you choose, for each vector space you choose a basis. And now if you have two spaces V and W, and then so you chose a basis, so you chose an isomorphism like this. And then there exists a unique map like this, such as this diagram is commutative. You just take the inverse of this isomorphism, so this isomorphism, this map, and this, the inverse of this isomorphism. And then you assign to a new map here, this map here, G. And this assignment is a functor now. Usually it's kind of counterintuitive when you want to. One good thing about categories is that it usually forbids you from doing arbitrary correspondence. Yes, when you define things in natural ways, and usually if you define functor, you don't really need to check that it actually makes morphism to morph. In fact, you even don't need to check that you know what to do with morphism once you construct it in a usual way logic. But here we use some choices, so it's a bit surprising that it actually will make composition to composition. But just check it, it's not that hard. Then see. That also is equipped with the basis. So this composition, if you know that this diagram is commutative and this diagram is commutative, then this large diagram is commutative. The outer diagram is commutative. No problem. So you construct the functor from vector spaces to numbers. No, the category of matrices, maybe better to call it like this. And okay, now it's very easy to check the experience of categories. So if you start from here, go here and back, then just identity is equal to identity. If you're starting from here, goes here and back, it's not equal to identity, because you start with vector space and you replace it by Rn. But it is isomorphic to identity because this vector space is isomorphic to Rn, and not in some way. You just chosen to define the functor you chose in some way. So you use this way that you chose, and this will give you the isomorphism of the competition to identity. Okay. So let us talk about. Okay, so this was a proof on your special case of the theorem, but you can add an exercise to the theorem for the general case. It's not hard. You need to use axiom of choice and so on. So let's talk about examples of faithful, fully faithful, and essentially social and yes. So usually when you if erase the diagram, I should have left it. When you forget something, structure and axioms, you get something functor which is fully faithful. Why? Because which is faithful. Why? Because everything every reasonable category, you have a faithful functor to set. All the forgetful functors to set is faithful because morphism of two objects with some additional sets with some additional structure, how you usually define it is a map between the sets that preserve the structure. So if you don't preserve, so if you forget the structure, then just map between the sets. So map between the sets that satisfy some condition is a subset map in a one-to-one way to just map between the sets. So all these forgetful functors are usually faithful. Otherwise, it's kind of weird to call them forgetful. Now, if you forgot some structure, then it means that you now require less thing for the map. So the map is one-to-one, but from maps, the functor induces one-to-one map from maps to maps, from morphisms to morphism, but not onto map, because you get some new morphisms that you didn't have before. For example, when you start with topological space for maps topology, now any map of set is allowed, also not discontinuous maps. If you don't forget structure, then usually if there is no structure to forget, if how the morphisms are defined, things that preserve the structure. If you didn't change the structure, then the morphisms are the same morphisms. You just change the axiom. But here you have to be careful because in the category of say monoids, you do require that unity goes to unity, even if unity was not part of your structure. So it means that it was not a good idea to say that unity is not part of your structure. Also, you're allowed to do it, but it's probably not a good idea. Yeah, so for abelian groups to groups, you have isofunctor. From groups to sets. So you're fully faithful, and this is just faithful. This of course also. Now another thing that I didn't say, two things that I didn't say. Two things. So first of all, fully faithful functor is injection on the level of isomorphism. Exercise if fully faithful, then isom f of the level of isomorphism. Yeah, so it's kind of funny because you added ontoness requirement on the morphisms and get one-to-one requirement on objects. This is what happens. And it's a very easy exercise. That's simple. You can start, you have an inverse in the target category, and you want to show that your original morphism is invertible. So you use the fact that every morphism in the target category is obtained, or some morphism in the original category, you're done. Another exercise is if you have it will be, and let's start full faithful, and then you can start the diagram. P prime, P prime. So you can construct, we like replace C with a new category, which is equivalent to it, and D with a new category which is equivalent to it. And here you have a C prime will be just a subcategory of B. And this diagram will be commutative. And commutative in what sense? So let's see. I think even on the notes, I'm not sure. So try to check if I need the exercise. And I think just that this composition equal to this. Anyhow, you can always use that this composition is equal to this. So you can do it both for faithful. So let's start with faithful. So you can do it for faithful, then this will be a subcategory. And you can do it for fully faithful. And then this will be the same construction that you did for faithful. This will become a full subcategory if this was a fully faithful count. So let's do example, and I think I talked about in the first lesson. You have what did you say there? Abelian groups and sets. And they say we can think of abelian groups as a subcategory, maybe not full, or not full of sets. And formally it's wrong because the same set can have two different structures of abelian groups. But let's talk about the following category. This final category, pairs. Yeah. Okay, we'll do it in two stages. So pairs sets. Okay, so just a category of abelian groups. So category whose objects are abelian groups, but maps are arbitrary maps of sets. So let's call it alpha. Objects are abelian groups and maps are just arbitrary maps. So we have a natural functor from here to here. And here we will have the category, let's call it sets prime, and category of sets such as there exists a structure of abelian group as this. Look weird, but we have such a people. So we have this functor. We just don't forget the structure of abelian group, but allow homomorphism. It's kind of forgetting functor. And this structure, we do forget our structure. Now I claim that I do also have this functor to sets. So this is just a full subcategory. Now I claim that this functor is fully faithful and essentially surjective. Fully faithful because it's so essentially surjective because it actually wants to available objects by definition. And essentially surjective, and fully faithful because we didn't change the morphisms. Yeah, here it's abelian groups and here the set the structure of abelian group sets the same. So this is the equivalence of category. So we can replay so if we consider now this functor so abelian groups so this is a subcategory, not full subcategory, but subcategory. And this is a subcategory. Here we just added morphisms, and here we just added objects. Yeah. So, okay, we didn't do exactly this, but we did something similar. We decompose our original functor from abelian groups to sets to embeddings, equivalences, and another. Now we want to get this thing. Let's do it. I want to replace, who I want to replace? I think I want to replace sets. Well, let's start with okay, if we just were interested in sets prime. We have abelian groups, function of the sets prime. And here we have A, B prime. And here we have abelian groups, identity. And here let's go to P, so here we have the inverse. So at least for this example of abelian groups mapped to sets prime, it's not all sets. We did construct such again. So we did replace this by equivalent category and this by equivalent category, such as this is prepared. And how we do it in general? So in general, we can say any set, we have two kinds of sets that have an abelian group structure and sets that does not have abelian group structure. What are the sets that do not have an abelian group structure? Any set of abelian group structure, am I right? Yes. I think I if you have, assuming it's the axiom of choice, so if you have infinite set, and then it's at the same cardinality as the sum of itself times this. So any infinite set have the same cardinality as this, and so it's have a bit of a structure. And then in finite set, you have just a cyclic order, a group of this order. So any set of abelian group structure. So if this is 1% forget about the thing. So touch any set of abelian group structure. So that's set and set prime are the same. So we need to do particular something. But maybe this time I got lucky. If there was some bad set that does not have abelian group structure, then I consider the following category. Let's call them bad sets. So category with objects are union of abelian groups and bad sets. But these are the objects, and morphisms are just morphisms between the corresponding sets ignoring the group structure. And then this category is equivalent to the category of sets. And it's included as a subcategory, the category of abelian. And you can play this trick in any case that you have a faithful functor. And so once you have faithful functor, you mean you can think about the category as subcategory, but not a full subcategory, which might be missing. And once you have fully faithful functor, it means that you can think of a category as a full subcategory, which actually a subcategory. And this was one outcome of this discussion. Another outcome is that if you add a structure, but you know it when you find morphism, then you could as well not add this structure. So there is no difference between the category of the metrizable topological spaces or metric spaces where morphisms are just continuous methods. Although formally they are different because metrizable spaces have different methods. But if you ignore this method when you define morphisms, then all the different methods will give you isomorphic object, and the two categories will be just equivalent. And this is sometimes a nice trick because, for example, you want to construct something for algebraic variety, and you know that algebraic varieties there are many definitions. But basically it means that locally they look like a fine variety, and the fine variety is something that look like a solution of polynomial equations inside a fine space of vector space. So there are lots of data that go into definition of a fine variety, which is not actually part of the structure. Yeah, so of algebraic variety. So algebraic variety admits some cover, and each of the open sets in the cover can be embedded into a finite space. It's a finite variety, so it can be embedded into a vector space. And moreover, you have some polynomials, some set of sequence of polynomials to define. So you usually don't want to use this data in order to define some constructions. But sometimes you feel that you have to, yes, because okay, you need to use somehow the fact that these guys exist, and sometimes the easiest way to use the fact that they exist is just to choose them and then do some constructions. So let's do this example. But somebody didn't know what our algebraic varieties is. I try to think, can I? Okay, so let me do simpler example. Groups. Finitely generated groups. So finitely generated groups is the last category. Or let's talk about finitely presented groups. Finitely presented groups. So the groups that say that you have a set of elements that generate this group, and the relations are also generated based on finite set of elements. Now you want to define some construction that starts with a group and give you something else. And suppose you need the fact that it's finitely presented. So you usually would use some generators relations to construct something. And then you can ask, okay, but if I didn't choose them, how I can still construct something? Then you can say, okay, nothing will depend on this construction. But what does nothing will depend? Start with the group G and construct some, I don't know, object A. You start with, but you needed to choose presentation of G. You do different presentation, you get an object A prime. Okay, but now why these two objects are the same? Okay, they're not the same. The objects in a category that always never will be the same, but they will be isomorphic. Okay, is it enough? No, you need to some procedure to choose this isomorphism. Is it enough? Also, no, I will say in a moment what is actually enough. But you don't want to, you want to have some finite list that you need to check. And even after you check it, at the end, you want to construct functors between groups to these objects, geometric objects. So how you do it? You talk about new category, presentations of groups. So presentation of group is like a group together with a set of generators and derivatives. And this category have a map to finitely presented groups. Have a functor finitely presented. Now this is not equivalence of categories if you define here like some reasonable notion of morphisms that know something about the presentation. But if you define this presentation of groups as a category of presentation groups with representations, and maps are just morphism between groups, then this is equivalence of categories. Now you have some category C, and now you can just construct a functor from here to C. Now you need to construct an actual functor, so you need to show that regardless of you can start with any presentation that you want, but if you have two groups with two different presentations and morphism between the group that doesn't care about the presentations, you need to construct a morphism in C and to construct a functor. And to show that this is a functor, so that behaves well with coefficients. But once you do it, you have a functor like this, and this is an invertible functor. Maybe you don't really know what is the inverse, but you know it is invertible. So you can take the composition and get the functor from the category of finitely presented groups to the category C. So in groups I didn't see it so too often, but in algebraic varieties I do see it often, so now you can ignore the next 2 minutes. So you can talk about, I don't know, presentation of algebraic variety. So it's algebraic variety X together with a cover that's equal to union Y and embedding UI into A and I into a finite space I, and together with actual equations that defines UI. So equations are like mapped to AM, so set of equations, and the UI is a fiber of 0, yes. So it's continuous square. So all this data, PI, and this is new I, So covering UI and phi, all this data is like presented algebraic variety, some data that you can actually put into a computer. And then you construct functor. You want to construct functor for algebraic varieties to some category. You can consider as a category of presented algebraic varieties and construct a functor from this category. As long as this is actual functor from this category, and in this category, maps are just things that completely ignore all this additional necessary data, you will actually have a functor from the category of algebraic varieties to your target category. And this I did so used. Very tiny. Now maybe a way to look at this construction under a microscope. Suppose you're not really interested in constructing a functor, but you do want to have a well-defined object. So you start with, say, let's go to this picture again, group with a presentation, and for each presentation you construct some object. And now you have two different presentations, and you want to show that the same object. So what actually you need in order to construct an actual object, and the data that you actually need is, though if you have some set of choices, I don't know what it choices, and you have some category C. So for each choice you want an object in C. For each two choices, so for each two choices, alpha and beta, you want isomorphism between phi of alpha and phi of beta. And for each three choices, alpha, beta, and gamma, let's call it C alpha beta. So you have this isomorphism, you have also this isomorphism, and you have this isomorphism, and you want your diagram will be complete. So once you have these three pieces of information, so for each choice an object, for each two choices isomorphism, and for each three choices, and this commutative diagram. So the diagram you already have from the second part, but you want it to be commutative. Then you can think that you construct an actual object in C. And so why it's two explanation. First explanation. So you can consider the category of all your choices. The category with objects are choices, and morphisms are just, there is one morphism between any two choices. And now you can consider the trivial category with just one object. And of course, the category of choices is mapped to the category of one object. And this functor is fully faithful and essentially surjective, which means that you have this equivalence of categories, so you have functor to the other direction. And now you have what you actually constructed here is functor of the category of choices to C. And then composing this functor with this inverse functor of this functor, you get a functor from the trivial category to C. And this is just an object in C. So this is one way to do it. But this is maybe not so satisfactory way because it uses the axiom of choice. So just choose one object for all the choices and say, okay, this is what I'm doing. It still makes sense because this, so you choose more than that. You choose one object and you just chose it. So this is one way to do it, but it's not really satisfactory because you use the axiom of choice. Another way to do it is take a limit. In this case, you can actually make it canonical, assuming that C is nice enough. So if C have limits, you can take a limit over all choices. And limit of this diagram, it doesn't really matter whether you take inverse limit or direct limit, because this is like full graph, or full graph is the same on both sides. So it takes a limit over all the choices. And this diagram, because for any two choices, you have both. And once you take the limit over all choices, you will get one object that really does not depend on any choice. Okay. Now I want to give non-trivial examples of equivalences. Something is missing here. Okay, maybe we'll get to it. So, no. Wait, break. So 15 minutes break and then the examples. Sure.
כאילו, זה טיפה משתיבות מקודם, סך הכל ההגדרות, לא תנאו בהגדרות. איפה, essentially more and subjective. ואיך הוא בדיוק הגיעו בהם? equivalence של קטגוריות? כן.
כלומר שאיזומורפית, אבל זה לא, כאילו שם.
לא, כאילו יש לך הכרה שהיא איזומורפית ל-identity factor, זה פשוט לוקח פה לעצמו, הומורפיזם עצמו, וזה איזומורפי מה שיש לך נשא טרנספורמיישן של איזומורפי. נראה לי.
כן, זהו לא בדיוק.
כן, כאילו, הוא ציפה כאילו שהתיאגול כבר נתן את זה. אבל אחרי שנות ההגדרות האלו, התחילו לקחת דוגמאות וטיפול.
לא, תשמע, כאילו קשה לי לדמיין עדיין השעות טרנספורמיישנס וככה. אז כאילו להגיד שעוד אחד הוא איזומורפי, ולהתחיל לתקף את זה קצת.
לא, אבל יש אינטואיציה, נגיד, כאילו מה שהוא עשה,
לא, יש שם הרבה אינטואיציה.
נגיד כזה choice equivalent לפשוט הסינגלטון, כאילו נכון? זה פשוט single choice, single object ו-single object. זה ניסן שזה
כן, אבל זה טוב, זה כאילו אתה צריך לקחת choice ספציפי עבור כל אובייקט.
אני לא עושה.
לא, כאילו זה ככה אני הבנתי את זה. עכשיו הבנתי נכון.
אני חושב שלא הבנתי נכון, כי גם אני חשבתי את זה, עד שהוא אמר ש-choice, הקטגוריה של choice equivalent של point, וזה, אוקיי, הבנתי שזה פשוט one choice. זה, you choose one object.
אבל אתה בוחר choice אחד מכל, כאילו מכל אובייקט אתה בוחר choice אחד. זה לא, אתה בוחר choice אחד. הוא אמר, אתה צריך להקסימום choice, זה לא סתם להדיפות.
לא, עושים של choice, זה פשוט לבחור אובייקט אחד וזהו. אני חושב.
יש את הדברים לדבר, בעצם לעשות שזה דברים אחרים. What is later? That's
מאוד ספציפי. אבל מה ברור ספציפי?
זה עם צ'ייסי.
שהוא הביא את זה בעצמו. שם. רק החצר לו שהוא ממליץ לו כבר.
איזה חמור, איזה חול למד את זה.
נראה לו פרופסור טוב. הוא איתם טוב.
אני לא יודע אם זה נחשב, אם אני הבא.
לא, עוד פעם, הנדעות בסדר, סבבה. אבל ברגע שהוא התחיל להדגים, היה המוח אף כן, אני ניסיתי, הלך. אבל כאילו,
לראות אם יחסית,
לא,
טבעיות, כאילו, הסנשי סרג'נטים. זה מה שהייתי קורא לזה כבר.
קובי, יש הרבה קטגוריות קודם, שהפנטום מביא שיש איזומורפיה, that's it. זה ליטיב סרג'קטיביטי עם one extra.
כן, רילקס סרג'קטיביטי.
כן,
אסנשל סרג'. that's it.
אבל פייפול ופולי פייפול זה כאילו, אוקיי, עם שם מוזר לעשות לך פה.
פייפול, אתה לא עושה קולאפס למורפיזם. ופולי פייפול זה שאתה באמת...
לכל מורפיזם יש יוניק מורפיזם
יש ממש יכול למצוא את הקטגוריה הזו. או, כאילו אסי.
לא את האובייקטים, את המורפיזם, כאילו כל זה הרבה המורפיזמים, הפייפול והפולי פייפול.
נכון, אבל כשאתה עושה משל המורפיזם, אתה עושה
לא, כאילו נגיד האקססס שהוא נתן. הוא עשה אחד למעלה פה, שהוא כזה, אם יש לך מפה שהיא פולי פייפול.
וגם...
לא, רק פולי פייפול. אז אם יש לך שתי אובייקטים איזומורפיים פה, אז ה-original images, כאילו ה-pre-images הם גם איזומורפיים. כאילו אם יש לך fx איזומורפי ל-y, אז x איזומורפי ל-y.
אבל בכיוון ההפוך, כי הכיוון אחד הדמיני יש לך. כאילו, כל פנקטור שומר בכיוון... כאילו של...
כן, אם x ו-y איזומורפים, אז x ו-y איזומורפים, אבל זה צריך להפוך. בגלל שאם זה fully faithful, אז אתה יודע שיש לך איזומורפיזם כאילו בדיוק שם, כאילו בקטגוריה שלך.
צריך לדעת, הכל בראש שלנו, אני לכתוב את זה. כאילו.
בוא נעשה את זה עכשיו. שטוש. ניקח את זה. אז כאילו שלנו אז מה שהוא רוצה זה שאם יש לך איזומורפיזם פה, אוקיי? והמפה היא fully faithful, אז יש לך איזומורפיזם פה. That's it, זה גם שזה. לכן כאילו, נגיד זה איזומורפיזם שקוראים לו פי, אז בגלל שזה fully faithful אתה יודע שזה שווה ל-f של l שם. וזה ה-f הזה בדיוק, שהוא גם איזומורפיזם. זהו. זה מה שאני אומר.
אוקיי, אבל... הפולי פייפול, הדבר הזה מתחיל כאלה כבר.
לא, הפולי פייפול פשוט אומר שלכל מורפיזם בין שתי האובייקטים האלה, כן? יש מורפיזם פה, ש-f של f של a, כאילו, והפוך, כאילו זה באיג'קשן, כאילו, זה בהכרחה
לא, זה לא, נכון, באיג'קשן. אוקיי, אבל לא זה מה שזה איזומורפיזם.
אז למה זה איזומורפיזם? אז כי יש לך העתקה הופכית, שאתה יודע שגם פה יש, נכון?
נכון, כי יש לך את הכיוון ההפוך, אז...
יש פי, וזה מעט ל-F,
כן, ובגלל שזה פנקטור הם חייבים לשמור.
כן, צריכים לשמור את הקומפוזיציה. והאידנטיטי זה האידנטיטי. זהו, זה.
כן, זה פשוט מסובך שאתה עושה כאילו לא מסובך, אבל אתה עושה קו, כאילו עכשיו שמים את האיזומורפיזם בכיוון אחד, אבל...
זהו, בשיעורי בית אני דווקא לא סימנתי את זה ככה. סימנתי את זה ככה. ככה סימנתי את זה. זה יותר הגיוני. עכשיו אני יודע את הכיוונים, כאילו. סוג כזה, אבל שיעורי בית עכשיו שנתקעתי, כאילו, שפשוט סלם נתקעתי, למרות שאני יודע את כל הדברים. מה אפשר לעשות ביחד?
זהו, באתי להציע. אני עוד לא עברתי עליהם, אבל אפשר... לבוא ביום... נגיד...
אני כמעט כל יום.
זהו, אני פה לא ביום ראשון, אבל אין בעיה, אם אתה רוצה ביום שני, שלישי. אני מתאים למרות שזה מתחיל להתקרב קצת בסוף.
מתי אתה בשלישי?
שלישי בעיקרון, אני מ-11 עד 11 הרצאה באחוז מדי.
הבנתי, אז לי פשוט ממש בבוקר יש.
זה כיף.
לי יש ב9 בערב.
אז זה הפוך.
זה יצא הפוך. אוקיי. נגיד שני.
שני אני יכול מ-11.
בסדר. יש לך הרצאה כאילו ב-10 או 9? אז אני מגיע ב-10. סבבה.
יש לך הרצאה לזה? שיהיו כאילו קצת פסומים?
לא, יום שני זה טכני יום חופשי, אני פשוט עדיין פרויקט קטן, אז אני עובד טיפה בפרויקט. אבל זה לא כזה הרבה... כאילו כל העבודה הקשה עשיתי בקיץ, עכשיו אני פשוט יותר לאחרונה של פרויקט. אז זה לא באמת ביום שני. לא ביום שני. לא גם אחרי ההרצאה הזו, אבל מוח נמס כבר.
כן, וגם אני לא ראיתי בדיוק את ה... אני רוצה לעבור קצת על ה...
אז בשני. מספר.
כן, אתה בקבוצה, אז פשוט...
כן, אבל אפילו את השם שלנו.
זה נכון, זה דבר ממש מדהים. אני תמיר ואתה... איליה.
זה אותך, ואני רק עובר את מספרים.
כן, אתה 1884. או שלא.
לא, זה לא אני.
יש עוד איליה. סילקמן.
כן, זה... ומה כביש?
יש לך עוד.
יש לך?
כן. אני תמיר.
סבבה.
אני מאוד...
כן, נעשה. המקסימום נמות ביחד. בסדר. ניתן נחמד למות ביחד משהו.
זה נכון.
מה היית לעשות בה?
יש מון 200.
אז
שום קשר.
שום קשר, שום קשר. אבל אז בכמה אתה?
אני בן 23.
אני 20. אני קיבלתי תואר מהצבא, רפואי.
אז רק עכשיו השתחררת.
אני?
כן.
כן. תודה.
אתה... כן, מסופר, עשית דחש, כן? סיימת את זה כבר שנה, סיימת את זה כבר שנה כבר יותר מידע ממני.
אפשר לשאול? כאילו אתה סיימת... אתה סיימת בגיל 19? עשית דחש ואז טסט?
כן, עשיתי דחש ואז קיבלתי תואר.
מעניין.
בסדר, היה מקרה רפואי.
Okay. So, where are we? Equivalences, examples of equivalences. But before, do we have any question? Still recording, yes, so it's time. questions? No question. Alright. Okay, so one equivalence that we already discussed is duality from vectors for finite dimensional vector spaces to its opposite vector. So this case is very like explicit equivalence. You have very nice functor to the other direction, the duality. You take twice the duality, and then you have very natural isomorphism functors on V so you for all vector spaces you have the duality functor. You always have isomorphism functors from so a composition of two countervariant functors with a covariant functor, just functor. And so you have this auto functor from spaces to self, the double dual. This set is this functor is not equivalent, not equal to identity, but if the vector spaces are finite dimensional, then it takes a morph to identity. Because so what this means is the functor is a morph to identity. You have identity, you have this functor. This you have this map, so this is morphism functors, and this morphism is an isomorphism functors with if the vector spaces are finite dimensional. And by the way, nice exercise that Shachar told me. You can go and you can ask what happens if to what extent this is not an isomorphism if V is not finite dimensional. And here is the way to do it. And maybe giving too much spoilers in this exercise. You can have two maps from here to the four times dual of V. Why? First of all, because V star star, let's call it W, you have a map from W to W star star. And the second thing that you have this map from V to V star star. Star star is a functor, so you can apply this functor from V to this map. So you get two upper different maps from V star star, V four stars. And are they different? So the question is, are they different? So let's ignore this thing now. The question is, are they the same or different? And we'll not say the answers to not spoil it too much. Not really at all. Category theory is something between category theory and linear algebra. We erase it because it's not part of the list. Okay, now other examples. Now I have to go to algebraic geometry. An example which is a very basic algebraic geometry, the category of affine algebraic varieties, and the category of the opposite category of commutative algebra. Yeah, so you probably want to solve this duality. If you start with affine algebraic variety, you can consider the algebra of regular functions from this variety to your thing. And you probably know that you have some correspondence. If you have ideals in your algebra, it corresponds to closed sets. If you have prime ideals, then it corresponds to irreducible sets. In fact, radical ideals correspond to closed sets, and non-radical ideals. Like you also can get a closed set, but it's not one-to-one correspondence. And basically you can encode all this knowledge in a simple statement that this functor is the equivalence of categories. Now, sometimes depending on how you define algebraic variety, so the definition that I like, which is the most intuitive one, so the category of affine algebraic varieties is actually category of subsets of CNs. Let's walk over C. So subsets of CN. So the objects are subsets of CNs, which are defined by a system of algebraic equations, system of polynomial equations. And morphisms are morphisms between the two ambient spaces, Cn and Ck, that maps. Morphisms are maps between these sets that can be extended to a polynomial map between the ambient spaces. So X here, Y here. So morphism are actual maps from here to here, such that there exists a map here, which makes the diagonal sets, yes. And this is not part of the structure. I mean, this is what actually defines the morphism, but we need to know that this exists. And it looks very concrete, and here we have something like very different. But in fact, so the trick here is that you, for any commutative algebra, with unity, of course, you choose generators and relations, or in fact, enough to choose generators. And once you have algebra with generators, you can reconstruct the variety X, because the generators you can think about them as basis vectors, and the relations will exactly give you the equations and defines it. And so what you actually do here, you form algebra. Fine. This is category of commutative algebras with sets of generators. So a different category, but it's equivalent because we ignore the set of generators. And what we actually show this is not with categories. But at the end you will have to prove something that the functors are fully faithful. I don't remember where you will have difficulty, probably in the fully faithful part. And when you see what actually going on, you will see that you actually need to use notion. So on the level of how to say token content, is this equivalence of categories? It's just a notion sense. Okay, another example of equivalence of categories, very similar example, is the Gelfand-Naimark theory or theorem. There are lots of different theorems which are related to this fact. I never saw it. They are like Nullstein and Sachs, but there are different formulations. So there is different Gelfand-Naimark, Gelfand-Mazur. So let's call it Gelfand-Naimark-Mazur theory that says that what? So you have the category of compact topological spaces, and you have the category of commutative, unital, and the categories are. So everybody knows what are C-star algebras? Who don't know?
C-star is the Riemann sphere?
No. C-star is very bad name.
Because C-star algebras.
Yes. Okay, so I should explain it. So what are Banach algebras? Everybody know? No. What are Banach spaces? So Banach algebra is a Banach space together with a multiplication map, which is like bounded. I don't remember exactly what you asked, but a posteriori just bounded both coordinates together and each coordinate separately for them. And C-star, so Banach algebras, C algebras are like Banach algebras over C we discussed, and C-star algebras are Banach algebras with additional structures that like resembles the bar operation for complex valued functions. So, and some structure which some map from the space to itself, which preserves the normal thing, and maps multiplication by scalar to multiplication by the opposite, by the conjugate. So and now the theorem is that compact topological spaces are the same as the category equivalent to to the opposite category of C-star algebras. And how do we prove it? So for any compact topological space, we can assign a C-star algebra of all functions. This continuous functions. Because it's a multiplication, it's Banach space, it's a multiplication
From the space to
to C.
You see?
So it's Banach space, it's have a multiplication, and it's have this bar construction because it functions to C. And how you go the other way around? So in fact, you don't really need to explicitly go the other way around. You just need to show that this is fully faithful and essentially surjective. But in this case, you have very nice sample around, which is for any commutative algebra with one, you assign the topological space of all its maxima ideals. So you know this algebra have a notion. So you know the notion of ideal. The collection of ideals have a natural topology, basically coming on from the fact that any okay. Okay, I want to go to details. Again, the key ingredient here, I think, is called Gelfand-Maddow theorem, that says that if you have a maxima ideal here, then the quotient by this maxima ideal is. And so we know that the quotient in the field, quotient by maxima ideal is always field, and the question is tells me that it's actually C. So another way to phrase it, so the quotient is a Banach algebra. It's a C-star algebra, which also a field. So C-star field. So the statement of Gelfand-Maddow theorem that a C-star algebra, which is a field, have to be actual C. So it means that anytime you have an element in a C-star algebra and the maxima ideal, you can get a number, just this element in the quotient. So any element in the C-star algebra gives you a function on the set of maxima ideals. And this function, you postulate that this function has to be a continuous function, and this gives you a topological structure on the set of maxima ideal.
Why does it have to be a C-star algebra for it to work? Why not? Why can't it be a Banach?
Commutative Banach algebra, probably a full two. Here. No, I don't remember. So
It will not work because it's a subset. It's a proper subset of this. It's not going to be also.
this algebra is not a subset, it's additional structure.
Yeah.
So
it can't.
so here it will not work with if you don't take this algebra because you need this structure. This I think it's just where you can have several different C-star structures, for example.
Yeah. Why do you need the conjugate structure?
So the idea is that if you have a continuous space, a topological space, and functions with value in C have inside them functions with real values. So here so another way to think about it is a complex space that came from some real space. So you could just do everything on the level of real numbers and then.
No, but you have this operation of conjugacy.
Yes.
Why do you need it?
So a posteriori, because if it's something comes from compact space, you have to have bar.
What? There's no natural bar structure on compact topological space.
No, but functions from them to C have bar structure because
From them
C
to
has bar.
C, but why do you need?
You can do everything over, but then it will be harder to formulate what exactly the structure on a real Banach algebra. So you can, instead of talking about C-star algebra, you can talk about real Banach algebra, such that after complexification, there will still be Banach.
Yes, but can't you talk about? Can't you do everything the same? But instead of talking about functions, continuous functions to C, talk about continuous functions to R.
You can do, but then you have to formulate the axioms a little bit more carefully. I don't remember exactly where, but you have to be careful there because you can have C. How I do it? So over R, might not have, the maximum ideas might not tell all the story. So I think it's something like this. When you consider C like a real algebra, it's not real valued functions in over any set. Yeah, so C as R algebra. So it's two-dimensional.
Mhm.
So if it's a real valued function over some set, the set has to have 2 points. But real valued functions over a set of 2 points is R plus R, which is not C.
Correct.
So if you just consider real algebras, you will not get, you will get some different picture. It will not be the same as the topological.
You're saying you used it in the way that maximal ideas, if you quotient by them,
Yeah,
you
so
always get
there is-
C.
Yes, the classification of maximal ideas over R is a little bit more complicated, and you have 2 types of maximal ideas. One that you quotient you get R, and one that you quotient you get C.
Mhm.
And over C there is one type. So you want to walk over C, but you want to remember that you came from R. And one way to do it is to say, okay, we have the star structure. Yes. You want to ask something?
I want to require that all algebras should be reduced.
That what?
Reduced.
Who actually?
All algebras. So they.
Like without importance?
Yeah.
You are right, but I think it's automatic in the Banach here, because otherwise it will not be Banach space, I think. I think the collection of all the important elements, I don't remember, but I think it just follows from the fact that it's a Banach algebra. We can discuss after the class, but
But we definitely need it in the case of.
yeah. Here, sorry. Also, yeah, I forgot many things. Final generator, then important. And unit. So unit are finally generated without importance, commutative algebras. So. So here I think it's automatic, and here the functor. So this procedure of taking the collection of all maximal ideals is sometimes called the spectrum. So we start with algebra, we take its spectrum, we get a topological space. Now here, in fact, I describe this as this opposite functor. I describe it not from this category, but from another category of algebras with generators, and then you have nice functor with other things. This is not the way it's usually done, because usually people define algebraic variety differently, a little bit more abstractly. And then the finite algebraic variety doesn't have to know how it is embedded to a finite space. Just have to have such embedded. But then you define algebraic variety is some topological vector, some topological space, not nice topological space like here, but there is topology, whatever, some weird topological space, such that there exists embedding into a finite space that satisfies some things. And then again, the procedure starting with commutative algebra and giving the actual finite variety is what's also called spectrum. You start with a collection of with your algebra, and then you take the collection of maximal ideals, and the collection of maximal ideals have a structure of algebraic variety. And now there is some confusion in notations. So you will read algebraic geometry if you read some classical books, or even modern books, but with classical theory. Say, take the book of Kempf, you probably will discuss the notion of spectrum. And the spectrum will be, I think it's there, will be the collection of maximal ideals. And when you read books about schemes, then suddenly spectrum is a collection of prime ideals. And sometimes people want to be careful, so they talk about spec P and spec F. This collection of prime ideals and this collection of maximal ideals. And kind of, I want to ask, so what is a spectrum given a ring or commutative algebra with one or with all conditions? What is algebraic variety which we have to assign to it? All the maximal ideals, or the prime ideals, or the maximal ideals? And I think the correct answer is both. And when you don't want So when you don't want to specify what you take, so in the modern language, you always do prime spectrum, and you write spec, you mean prime spectrum. This is like one correct answer. But I prefer a little bit different point of view. So when you don't want to specify what you use the word spectrum. And what do I mean by that? So you have the category of affine schemes, maybe, which is more general objects than affine algebraic varieties. And inside it, you have subcategory of affine algebraic varieties. Inside, they mean that you have a fully factored functor axis. And you have the category of rings and commutative rings, and this category of unit with all the conditions, which is certainly subcategory of the category of all of this. And here you have a functor which we can call spectrum, and here we have a functor which we can call spectrum. And both these functors are, this diagram is commutative. So these two functors are compatible, so it's perfectly okay to call both of them spectrum. Now, any affine algebraic variety is also an actual set. So you can, especially if you're working over C, you can just touch all the points, solution of these equations. And you can define a affine algebraic variety like set with additional structure. And one of these structures is topology, so you have forget a functor from here to topological spaces, which is often denoted by the absolute value C. Now, if you know what is a scheme, you can, when you will read some textbooks, you will see that scheme is also a topological space with some additional structure, some long story. So you will again write top, and you also have such. And now this diagram, this diagram is not commutative. So when you have a affine variety, and you consider it as a affine scheme, and then ask what is the topological space, you will get different answer when you do it directly. So you can choose to redefine this functor, this composition, but then you will get very different space. So it will not be the collection of all solutions. It will be something extremely active. So I can say what it is. So suppose you have, I don't know, x squared plus y squared is equal to 1. So the collection of all solutions of the circle. So in this case, it will not be extremely ugly. So the answer is the topological space that you will get when you go like this. It will be the entire circle, but another point which is kind of infinitely close to all these points. So its closure going to be everything. It will not be half surface. It will not be epsilon. And now if you take something more ugly, for example, no equations and two variables, so basically the entire plane, then if you do it in classical language, the affine algebraic variety as set will be over here, will be just a C squared, the plane over C. And here you will get some disaster. You will get all the plane over C, but also for any irreducible algebraic curve, anytime you have like irreducible polynomial which defines the curve, for this curve you attach an additional point which is kind of infinitely close to all these points, like all the topological space. And also you get another point which is called the generic point, which is infinitely close to all points in the space. So you can go like this, but you get something a little bit unexpected. And this is exactly the difference between spec M and spec C. So I prefer to think about spec M as this composition, and spec P as this. So all these ugly spaces are what happens when you consider all the prime ideals. Yes, what are all the prime ideals in the ring of polynomial in two variables? So you have the maximum ideals, but you have other ideals too. You have the ideal 0, and you have ideas that are generated by one polynomial that happens to be prime, something prime. And those are all these ugly points, which are called generic points. So spec M and spec. So I prefer not to think about two different things, spec P and spec M, and spec you have to decide what you choose, but three different things, and they're all well defined. spec P and spec M, they start with an algebra, a ring or whatever, and give you a topological space, a set of topological space. And spec start with an algebra and give you a variety or a scheme. And then the spec is well defined. It can be even when you consider the variety, or you can consider a variety as scheme is well defined. But the question of what is an actual topological space that corresponds to a variety, it's not well defined. It depends if you consider the algebraic variety or others. Okay. So
But also just because we want to remember an algebra of functions,
what do you mean?
regular functions. No, I think
The idea is that they're both opposite to the construction of taking the algebra of functions. Spec is the inverse functor of the functor that start with a algebraic variety or algebraic scheme and give you the algebra of functions. So, fine, variety. So spec is this inverse, and the spec P and spec M is when you compose them with this functor that actually give you a set which you can touch. And you can define this composition directly, and spec is kind of more complicated construction because spec is an algebraic variety, so you have to define what is algebraic variety. Spec M, you don't need to know what is algebraic variety, it's just a collection of all maximal ideals, just a set. If you want, you can put any topology. Spec P is just a collection of all prime ideals. You don't need to know what algebraic variety is to define. Okay, here is a nice example. So remember when we talked about the category that corresponds to a group, category with one object and the group has automorphism. Now I said that we have kind of this dichotomy between categories which are like resemble some theory and categories which are kind of combinatorial things like groups. But this dichotomy is not actual dichotomy, so there is some things in the middle. So in fact, sometimes you can think about the same category in both ways. So here is an example, the category of G principal spaces. So what is G principal space? Definition G space is a set X on which G acts such that so the action is simple and transitive, so it's transitive and the centralized of an stabilizer of element is trivial. So such that I've we know that by transitive I mean that it's also non can find transitive in different ways, so I want it to be. And now you have the category of all G sets. We don't remember we gave this example or not probably did, but it will give it now. So given a group G, we can consider the category of G sets. Sets and G sets on which G acts, and the maps should of course preserve the action of G. And inside this category, we have the full subcategory of G principal spaces. Theorem, this full subcategory is equivalent to the category of BG. So, theorem G places equivalent, so this is not equivalence of mathematical statements but of categories to BG. BG is a category which have one object and G as. So let's see where it's easier to make the functor, of course, from here to here. We're given so we have just one object, we need to decide to what G principal space to send it. So do we have suggestions? No suggestions? we start with this category, which have one object, and we need to find some one G principal space. I'm sure that you all have the favorite G principal space.
Take G.
What?
Take G.
G.
The action of G on the set.
Okay. What action?
Just left multiple.
Left multiplication. So now I know what you prefer, left right. But now all mathematicians somehow will choose left multiplication. Yeah. Action itself from product with on the left. So you can mesh the all the objects here to this, and now what you do when you have two morphism here, so two objects here, which is just the same object, an element in G, where do you map it?
The action.
What do you mean?
Yeah,
What is
itself.
the morphism?
Yes, I need to define a functor. So it says the action, which is a good idea. So you have the same object, so G acts on itself, and then you say element G and say, okay, let's act on it on G. But this is not morphism of G principal spaces, not morphism of G sets. So you need to tweak it a little. So maybe I was wrong. Maybe you didn't prefer left, you didn't prefer right, that you wanted the morphism, we go to the right application. So if your sets are left action, then the morphism between G principal, the G as a G set to itself are exactly multiplication by a right from the right by an element of G. So we still can decide. We have two pictures, but they both have left and right in them. So you can do for the other equivalents, they're both the same. And just you have to be careful when you take action from G principal set with action from the right. The action from the right is still a left action because when you say G sets, you usually do the actions of left action. So left action means that you act with G units. And here also, where you have G, I think you also have, you want it to be homomorphism. So you want to act with G inverse and not with G from the right. Okay, so very good. So you have a functor from here to here, and this functor is fully faithful and essentially surjective. So the full part of fully faithful is not completely obvious. You need to actually show that any map of G spaces from G to itself is given by a multiplication by element from the right. And this is very easy, you just take, you ask where you map one, and then you just determine that. And this means that this functor equivalence of categories, but the functor to the other direction is bad. You need to choose. So what you actually need to choose for any G principal space, you need to choose isomorphism between this G principal set and the standard one, G actual. And the one that you choose, you just choose a point. How you choose such isomorphism, you just have to choose a point in G principal space, and there is no canonical way to do it, because okay, this idea G principal space is not G, it's something with a free G action. A simple time with G action. So this is it. Questions?
So you need to compose the morphism from right. You multiply from right, and then you compose the morphism from left, or whatever said. Like, how do you construct it?
How do you construct the functor to the other direction?
Yeah, to the more
Once you show, so once you show the point, then okay, so on the level of objects, it's clear that for any object here, there's only one thing you can do. Now we have morphism between two sets, and you want to assign element in G. So you compare it to there is a unique morphism that maps a special point to a special point, a chosen point to a chosen point, and your morphism is this thing times multiplication from the right by G inverse for some G. So you take this G. But usually you don't really need to care. Once you have functors of one direction, fully faithful essentially subjective, you know it's in its equivalence of category and you don't care. Now
We constructed a functor from BG to the functors from BG to sets, right?
functor
Because
from
we
no
said we just-
G principal spaces are
Principal spaces is just
you
a
can see
category,
vertically,
you know?
but yes, you're right. But no, it's not from BG to sets. It is from BG to sets, but we didn't say it yet, so you're jumping ahead. 5 lectures ahead, probably, or 7 lectures ahead. So
So
let's.
It's nothing we see and I don't know.
Can you consider it as a subset, special case of your dilemma? Probably yes. Now you jump only 1 lecture ahead. Okay, this is better to discuss after that. Not during the lectures when we get there. In Galois space, so Galois correspondence. Okay, so maybe Galois theory is historically the first place when you have some kind of correspondence that resemble functors. So it's a bit degenerate example from the point of view of category theory, but it's like historically the first. So we have so we have a field K, and we can look into the category field potential of K. So they're not all the morphisms are monomorphisms, but this is it. And now you have category from here to groups. This category, this functor from here to the category of groups, just taking a Galois group. So this is dot equivalence of categories. And how do you make it equivalence of? So it's contravariant functor first of all. So any extension gives you its Galois group. And how do you make it equivalence of categories? So of course here you have to take all the Galois extensions in order to it make sense. And then here you have to consider these groups as like the under category, or even less than that. So you take the absolute Galois group, K bar over K, and maybe I have a better explanation. No, let's do it like this. And K bar over K, and you take this Galois group, and you take the category of all groups together with an onto map from this. And then you will get equivalence of category, which is a content of a Galois theorem. So let's try to make it, I think, a little bit more elegant in the case of topological spaces and coverings. So you probably know, so if you took some course in algebraic topology, you probably notice that there is some analogy, and sometimes it goes beyond just analogy, between covering of topological spaces and Galois theory. So let's talk about this thing for Galois for covering of topological spaces. So you have the category of covering of X, and you have the category of group. So for now, assume that X is in connected space, and not just connected, but also pointed topological space. Connected pointed topological space. When I say connected, so I want path connected, and I probably want like also locally simply connected or some other nice properties. Oh, say locally contracted, but nice topological space. And then I claim that you have, no, I don't want groups, so I want X. Oh, I want this factor. So what is phi1 of X, everybody know? And now you have sets of these groups, so group sets with action of phi1. And they claim that I have equivalence of categories between the category of covering of X and the category of sets of phi1 of X. And how do we define these equivalence categories? So for if we have a covering of a point in set X, we have, I think it's called deck transformation. So if we have covering and we have a pass starting with the threshold point x0 to itself, we can lift this pass uniquely, and we have a point in the pre-image of x0. We can lift this pass uniquely, unless we follow this pass over the covering, and we get a pass which lies over this pass and goes back to some point over x0, but not necessarily x. So it means that each pass in pi1, each element in pi1 acts on the fiber. So what is the assignment? So if we have covering y x, we assign to it by inverse of x. So this is a set, and this set has a structure of topological space. And this set has a structure of pi1 set. So we got a functor. And the claim is that this functor is an equivalence of categories. And this is true not for all topological spaces, but they have to be nice enough because we want to prove that this is essentially surjective. And so we need some way to actually construct a covering starting with a set. And okay, for this we need some assumption of the space. Now, if you want to consider only connected coverings, then what set you will have to get here? What is pi1 sets you will get here? How?
Could you repeat the question?
If I want to consider only connected coverings, what pi1 sets I will get here?
Probably all the plans.
Transitive, yeah, probably you can call it also this one. Transitive sets. Transitive sets. Why? Because if this is connected, so it means that for any 2 points in the fiber, you can connect them with a path. So you can project this path downstairs, you get a loop downstairs, and this exactly gives you the element by one that maps one to that. So connected coverings correspond to covering sets. Now, if you want to consider pointed coverings, so coverings which also have chosen point here, what you will get here? Pointed coverings. So you have points. This point has to be in the fiber of L0 because it has to be a map of pointed sets. So here you will get pointed transitive sets. What are pointed transitive sets? How you can describe all the pointed transitive sets? Probably should have started with this example. So let's. So just take this example. I'll just close this story. What?
It just goes in front of the loop.
Exactly. So transitive pointed sets all can be transitive sets can be all obtained as a quotient of a group by a subgroup, but not in a unique way because you can choose different points. But if you have transitive pointed sets, so you have a canonical way to present it as a quotient by a subgroup. In other words, we have the category of transitive pointed G sets, and you have the poset of subgroups of G. And you remember that posets also a category, so you take subgroup of G. What was this? Subgroups of G. This is a poset, but you can consider it as a category, and you can take the opposite poset and as the opposite category, sorry, you can also take the opposite poset, never mind. And then you have a functor, the natural functor is from here for any subgroup you can consider the quotient, and you see that it's reversed the order. Yes, if you quotient by something large, you get smaller set. And this functor is fully faithful and essentially surjective, so it is equivalence of categories. And transitive pointed spaces are the same, like connected pointer others of the bus. So we get that this category, oh, maybe the natural error is this category is equivalent to this category. And in fact, it's kind of not natural to get map for any direction to any direction. You don't really need the axiom of choice because here you probably can do the opposite thing without axiom of choice. But anyhow, the nature of the structures are like this, but you've got an equivalence to this category to this category. And now we can go back to the Galois example, so field examples. So probably ignore what I said before about it. Extension of field K. And they behave like transitive pointed covering of something, whatever something means. And this category is actually equivalent to, you don't take Galois extension, you can take all of them. And this is subgroups of K bar. Okay, I have more examples, but for not too much more. No. Questions? Okay, see you next week.